this plasma is made of gas molecule, excited gas molecule. That is actually, you can see that this, I mean, asterisk symbol is given, and this is actually very important. It has very important role. Then there are actually this blue color, sorry, green color region. That is actually, sometimes it could be plus charge ion, and it could be free electron and some molecule fragments. Okay, so that entire combination, I mean, entire whatever that is mentioned here, all the things actually will consist of plasma. And this plasma, of course, will have very high energy, and that is actually, we can say it's a fourth state of matter. Now, in our nature, actually, there are so many plasmas are there, and if you see the temperature, and this is number density, charge particle per meter cube. So this is actually lightning. So we are familiar. So why lightning is happening? Basically, that this inside that when cloud, there is accumulation of the cloud, and what will happen that its charge, I mean, it's actually charge particle actually will reach there, and it will need to get a path to discharge. Okay, and this is like that in the cloud actually. So discharge path is nothing but that some short circuit line, and that is appear as a lightning. Okay, and I mean, if you know that in Western Ghats some area is actually very prone to lightning because their soil or the rock contains huge amount of hematite or magnetite. So that's why this particular short circuit path in between the cloud and the ground become easier. So that's why though some places are there in Western Ghats where lightning actually very frequently happening. Okay, so then the lightning actually is in what will happen? So in between the cloud and ground, in between, that some localized plasma state will generate, and through there actually that there are actually some conduction path will generate, and this lightning will touch to that ground. Okay, ground or maybe sometimes some surface that we can see sometimes the lightning catch, I mean hit on a tree, and the tree actually burned, so that through the tree actually got the path to reach to this earth surface. So that is actually one example. Similar solar core and plenty of other examples are there, the plasma. So that we can imagine that what could be the temperature of this lightning, because all are afraid of this lightning because there is a huge energy is there. So if you have some capability to store this energy, maybe we will have a very, I mean, high energy. Okay, but that is actually still some lot of research is going on, but it's not yet successful yet. So one thing is clear. So if we generate the fourth state of matter, energy will be very high. So now question is that this fourth state of matter, how can be used for, I mean, different applications. So now this, let's come to this plasma. As I told, this is actually solid ice. You can see the liquid, then it's a gaseous state, and further if you make it ionized gas, then we can reach to that state of plasma. So plasma from this Greek, I mean ancient Greek, meaning that moldable substance, and it's one of these four fundamental state of matter, and was first described by Langmuir in 1920. And it consists of a gas of ions, atoms, which have some of their orbital electron removed, and this and free electron. Okay, so this consists of a gas ion, atoms, which have some of this orbital electron removed, and the free electron. And then this plasma can be artificially generated by heating the substrate, a neutral gas, to a strong electromagnetic field to the point where that ionized gas substance became increasingly electrically conductive. Okay, so then this plasma can be generated So if you have actually, it's kind of two electrode, so in between the two electrode, whatever that in between the gas, if you generate a field in between the two electrode, that whatever the gas in between, it can be ionized. So now let's come to this sputtering process. So in sputtering, what is happening? That we need to generate this plasma. So where this plasma will generate? So this is actually how is this. Maybe yeah, this first I'll go to this slide and then come back. So this is actually one plasma chamber. This is actually, you can say, modified version of physical vapor deposition. So in physical vapor deposition, what we are doing, the melting and then evaporation. But in this case, actually, what is happening? This is RF generator, and using this RF generator, and this is actually substrate, and this is target material, and this substrate side. So this is actually this target. So target side actually it will be cathode, and this is wherever this which substrate you need to deposit. Okay, so this is this is the substrate and this is the target. So target will be cathode side, and substrate should be in that anode side. And from this cathode side, you can see these atoms are actually coming. But how these atoms are coming? So what will happen that if you put a argon gas, and then what if you do that, make it argon ionized, then this ionized, that is this plus charge, it will actually move towards this moves towards that cathode, and it will knock on that cathode surface some of this, due to its actually high velocity, some of this atom will ejected from the surface, and those ejected atom will come and deposit or condense on that substrate. So that means you need to, so this color represent the plasma, okay, and there is a strong electric field, of course, you need to apply to generate this plasma. So that means this is a substrate holder, and substrate or anode side should be, it should be grounded, and this is actually that vacuum pump action. So of course, at the beginning we should have a vacuum. So in this case, how to start? Like this is cathode side. So cathode side, you need to put a target material. Let's say you want to deposit L2O3. So in that cathode side, this is your target material. So this should be pure L2O3. So first you have to fix it in this side. Then substrate you have to fix it on this substrate holder. Now next job is that you have to do the vacuum. When you achieve sufficient vacuum, then you purge little bit this working gas. Most of the cases argon is being used. Then that this electric field as well as in magnetic field, that is for magnetron sputtering. So in electric field in general is being applied, and due to this electric field, so there is a generation of this plasma, and when plasma will generate, whatever that argon we are purging through this as a working gas chamber, this argon will convert to argon plus, and that argon plus will be heating on this target surface, and when it will heat, it will eject, it will actually eject that this one, that blue color, that is actually sputtered atom from this L2O3 target surface, and those are coming on this on the surface. Now you might be thinking that even it's knocking on this L2O3 surface, aluminum and oxygen, both atom will come. So what will happen that there is a, when there will be a knocking, so both atom will come and it will deposit on the target surface, maintaining that similar stoichiometry. So now question is that in physical vapor deposition, we have seen in PVD, melting of Al2O3 requires 2054 degrees Celsius. So that is actually very difficult sometimes to melt that material. But in case of sputtering, it's not a big deal. So whatever limitation we found in physical vapor deposition, some of the limitation can be overcome by this sputtering technique. Here again, that with that schematic, it will be better clarity will be there. So this is the target. So this is target cathode, and this is actually this other side of the electrode. So like this is anode side, and this is the substrate where material where you need to make a deposition on top of this material. And here you can see the target atom is black color. This free electron, that is actually that blue colored dot, and target atom you can see it's actually ejecting from this target surface and it's continuously coming to this substrate side. And then free electron, you can see those free electrons are actually at the vicinity of this target material. And this electron, what is the role of this electron? This electron will hit that argon and it will continuously keep on making this process of argon to argon plus. And this argon plus will hit on this surface, and then this atom from this target surface will be ejected, and this atom now it will deposit on this surface. So any questions so far? Any questions so far? Okay. Now in this sputtering process, what is happening that as I told that one should be target material and target should be the same material of whatever you want to deposit. So that is a big challenge. So first you have to prepare the target material, and generally people how they used to do, like let's say that alumina you want to deposit, so pure alumina powder you have to take, you have to press it, you have to make a pellet, and those big size, according to that, size of this target holder, so that size actually you need to prepare, and then you need to compaction and then sintering, and those material for oxide, in case of oxide you have to keep it on the target side. So in that, let's understand the sputtering process. The plasma is needed to make the gas conductive, and generated ion can then be accelerated to strike that target. So target material, so whatever that actually generated ion, then the rate will accelerated and it will strike to the target. Higher pressure than this evaporation. So of course there will be slightly higher pressure, because as I told, after reaching that substrate sufficient vacuum, then you need to pass this working gas. So when you pass the working gas, what will happen? Then some pressure will fall. So higher pressure than this evaporation, and better at depositing alloys and compounds and evaporation. So similar for alloy also, we have seen that in case of alloy, there is a keep on changing the composition. And that's why, suppose one particular document you want to deposit in physical paper deposition, you are required, like you should have, I mean, if you use one single alloy, that composition should be entirely different according to that calculation, or you have to use two different board. So then this plasma contain equal number of positive argon ion and electron as well as neutral argon atom, and typically only 0.01% atoms are ionized. So less than 0.01% of atom are ionized, and there only huge amount of plasma is actually being generated. Okay, so now this plasma process can be divided into four categories: DC plasma, AC plasma, and AC actually alternate voltage when it's applied, mostly the radio frequency, then reactive plasma, and fourth one is that magneton sputtering. So this magneton sputtering is actually most efficient, and that's why it became very popular. So most of the places you may get this, I mean, magneton sputtering, this one. So DC and AC, what is happening? So there will be a cathode side and anode side. So anode side you have to make the deposition, substrate will be there, cathode side target, and there will be a bias generation will be there. And like DC plasma mostly used for metal deposition, because in metal deposition you need not to be bothered about because all are same kind of atom. But in case of oxides or like halide, a metal halide, so they are actually, I mean, so mostly that oxides or sulfides actually, different kind of atoms are there. So in that case, this AC is more preferable. So in AC actually I'll talk about what are the advantages of why AC actually this is. AC pulse will be applied in between this cathode and anode. Third one is the reactive sputtering. So in reactive sputtering, what will happen? Inert gas plus the reactive gas is purged, and here plasma will generate, and there actually due to this temperature and this reactive, I mean gas, whatever gas is there, that is actually from this metal target, it will actually it will take some atom from there itself and deposit on this, I mean, substrate side. And fourth one is the magneton sputtering. So in magneton sputtering, so magnetic field is there. The magnetic field purpose is there to confine the electron in the close vicinity of this substrate, because this argon, as I told, that one role of this particular free electron is to convert argon to argon plus. Okay, so this argon to argon plus process actually should be continued. Otherwise, what will happen after some time, that you can see that your sputtering actually is decreasing. The rate of deposition is decreasing because maybe sometimes there is not enough number of argon is there in the chamber. And this sputtering process can be used that actually for two purposes. One is actually the sputtering for film deposition. So the sputtered atom may be deposited on a substrate surface for film deposition. So as already we explained from the target, that atom will be ejected, and those ejected atom will deposit on this substrate. So this is actually the sputtered atom may be deposited on a substrate surface for film deposition. Second, that sputtering for etching. So that is also can be used. So sample can be displayed on the target for etching. So like example is the plasma etching, dry etching, reactive ion etching. So whatever that ionized gas or this ionized plasma is being generated, those are actually ejected on some surface so that it can do some selective area etching. So in this case actually is a totally opposite. So previous case you can see from the target atom is actually basically coming and sitting here at C. But in this case directly that this whatever this ejection is there atom, and there is some whatever that you desired shape or desired that etching, I mean surface, each surface you may get it. Now this spartering actually has some advantages, and that's why this technique became very popular. And what are these advantages? Able to deposit wide variety of metal, insulated alloys and composite. That is actually huge advantage. So metal is easier in PVD as well as in sputtering. But if you go for alloy, then intermetallics or maybe sometimes that oxides, then it will be a real challenge will be there in physical paper deposition. Replication of this target composition in deposited material. So whatever that composition is there in target material, deposited film will retain that composition, capable of in situ cleaning prior to film deposition by this reversing the potential on this electrode. So this is a unique advantage. So like actually if you want to do some cleaning on this surface prior to the deposition, so that is also possible that if you change this potential on the electrodes, for what will happen that I mean charge and heat on the substrate, and they are actually I mean it may clean the substrate. Better quality film and the step coverage than the evaporation, and this is partly because the atoms are more energetic and the film is described by in situ ion bombardment, and it is easier to heat up to higher than evaporation than is in vacuum. Okay, and this reproducible the deposition control, the sample thickness, rate, sample process, these are things. And this just to please go through that can use a large area target for uniform thickness over the large substrate, and sufficiently that target a sufficient target material for means many depositions. Once you make the target, several deposition can be done without changing that target. And this no extra damage that is also is there. Some of the challenges like substrate damage due to ion bombardment or this UV generated by this plasma. These are the drawback. Higher pressure. So higher pressure means more contamination unless using ultra clean gases or ultra clean target. So in these two areas you have to be very careful. Ultra clean gases and or ultra clean target. So these two things is basically helping in doing the deposition. Deposition rate is some materials quite slow and some materials that degrade due to ionic bombardment, and most of this energy incident on the target become heat which must be removed. So there actually some heating will be there. So like PVD here also some cooling continuous cooling arrangement will be there to cool down the temperature of the target. So these are actually some of the things. And now if we compare with the vacuum processing, so what are the difficulty you are facing in vacuum processing, and that can be overcome here. So use high temperature at high vacuum to evaporate atom and the molecule of a material surface. Okay. So here we need a melting and the evaporation of the material. So this part is actually is not required. So we there in physical paper deposition you need to do the resistivity to generate this very high temperature, so that most of the means respective material or metal will melt. So that is actually not required melt or sublime. And there are very few things that rate and the substrate temperature one can do to tailor the film property. So there actually this only the rate and substrate temperature, two things are there to tailor the property, but in PVD there are plenty of other parameters are there can directly contribute to this good quality of the film and use the ballistic flow to transport them to the substrate and this deposit. Okay, so this is actually already we have seen that in vacuum deposition, how is the flow pattern, and this step coverage is poor in case of physical vapor deposition. So there is absolutely no problem in case of sputtering, and it is not suitable for compound or alloy deposition in PVD. And considerable materials are deposited on chamber wall and wasted. So these all the things actually can be overcome. In this case. Okay, so with this one, just I like to wrap up. And next class, I'll talk about this how this sputtering process. So if you have any first question, please to ask. In the meantime, I'll take the attendance. So if you not have any questions, I am asking one question. Like in sputtering, can you give any example that where sputtering is being used rather than the film deposition? Can anyone tell? Rather than the deposition, like any other cases, can be sputtering can be used? Application of sputtering. One is actually you want to if you want to deposit. I mean, any other. I mean, so what are the? Can anyone tell? Like I want to make a deposit or I want to make a protective coating kind of thing. I am using the pattern. I mean sputtering. Any characterization unit we need the sputtering? Puja? Can anyone? Utsav?
So it's used in semiconductors. So coating for semiconductors.
No, that is okay. Which characterization unit do we need the sputtering? In metallurgy, used in metallurgy, where sputtering is being used. In which characterization you need to make your surface conducting? Please.
Sir, an
So
SEM.
circuit boards.
Yeah, circuit board, that is okay. In metallurgy, that like if you do that scanning electron microscopy, so your scanning electron microscopy sample, that surface should be conducting. And that is actually how do you do? Like in along with actually this scanning electron microscopy chamber, there will be a separate sputtering chamber. Now another question I'm asking, which metal is being used to deposit in case of scanning electron microscopy? Nitin?
Gold. Gold.
Correct.
Gold.
Yes. So gold is being used to make that surface conducting to in order to observe the surface by scanning electron microscopy. Okay, so with this I just finish it, and this Thursday we shall have a quiz. Utsav, it is fine.
Yes, sir, it's fine. Or what's the syllabus, sir?
Syllabus means up to the Thursday's class. Up
To
to
Thursday's
next
class will be
class.
the
Yeah, up to
topic.
next class. Next class. Okay. Yeah.
Yeah, perfect.
And when
Thanks,
is my this mid-sem? Till now schedule has not come yet.
So we haven't received any schedule yet.
Okay, fine, no problem.
I will let you
Okay.
know.
Yeah, fine. Thank you. No, actually, I am happy that how you are coordinating in
Okay.
this class. Very good.
Okay, sir.
Okay, then. Thank you. Bye.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.